I'm Rocky Cobb, Dean of the Division of the Physical Sciences at the University of Chicago, and it's been my pleasure to serve in that role for the past 5 years, and will be for the next 44 days, 5 hours, 55 minutes, and 12 seconds. I'd like to, first of all, express my thanks to President Elisa Tenney and her staff here at the School of the Art Institute for their gracious and important partnership we have on the lecture and on other activities we do with them. This collaboration between our department and the School of the Art Institute started about 10 years ago through our mutual friendship with Barry McLean. This is a Barry McLean building, and was supported for many years by another president of the School of the Art Institute, Walter Massey. So thank you, President Tenney, for your continued support. It's been my honor to be part of the Brinson Lectures since its inception 10 years ago. And if you look through the program, you'll see the speakers we have brought here have world-renowned expertise, and including our inaugural speaker, Wendy Friedman, who, by the way, is now part of our Astronomy and Astrophysics department and is here this evening. And our second speaker in the series, Kip Thorne, who followed Wendy, won the Nobel Prize last year. Giving the Brinson Lecture is now considered a prerequisite for the Nobel Prize. Now, I could tell many stories about all of the rest of the lecturers, but we're here tonight to hear from another great lecturer. Before I ask John Karlstrom to introduce Professor Ellis, I wanted to take a moment to acknowledge the generosity and support of the Brinson Foundation, and particularly Gary and Suzanne Brinson, who are here this evening. Could you please stand? It's now my pleasure to introduce John Karlstrom, who will introduce our speaker. John is a Subramanian Chandrasekhar Distinguished Professor in the Department of Astronomy and Astrophysics, the Department of Physics, the Enrico Fermi Institute, the Kavli Institute for Cosmological Physics, and the college. The font on his business card is really tiny. He's currently the director of the 10-meter South Pole Telescope, and he's leading the effort to build the next big cosmic microwave background telescope. And in his spare time, he's now chair of the Department of Astronomy and Astrophysics. John?
Thanks, Rocky. When you're done with being dean, you've been a great dean, but we could really use some help in the department, so we're looking forward to that. So I want to add my welcome to all of you here tonight. I know it's a beautiful day. There are many places you could be, but I think you'll find that you made the right choice. You won't regret being here. It looks like a fantastic evening. And I also want to point out before I forget that if you open your program, there's a small card in there. That's to help us find out how you found out about this so we can promote these events even better in the future. So please fill that out and just drop it off with anybody. Anyway, through these Brinson lectures, the Department of Astronomy and Astrophysics has linked our audiences with the world's, as Rocky said, the world's foremost authorities in the field. All right, each one has brought a unique perspective to very exciting topics that you can see listed on your program. It's really been terrific. They do a remarkable job of helping our audience understand the complexities of their work, but also in bringing all of us up to the frontier, to the cutting edge of astrophysics. All of us, including me, to hear what they're doing. It's fantastic. Richard Ellis is no exception to this. He's here with us this evening from the UK, where he's professor of astrophysics at University College London. He spent 16 years at Caltech, and for a large fraction of that time was director of their observatories. He works principally on observational astrophysics and cosmology. He goes to the telescopes. He uses the world's largest telescopes and even the telescopes in space to peer back in time to when the universe was just a few % of its present age, and I'll let him explain that to you. He's a recipient of numerous awards and prizes, including the Carl Sagan Memorial Award, the Breakthrough Prize in Fundamental Physics, and the Gold Medal from the Royal Astronomical Society. That's just to name a few. He was a member of the Supernova Cosmology Project, whose discovery of the accelerating expansion of the universe. It's not enough that it accelerates, that it expands, but it's actually accelerating in its expansion. And that led to the 2011 Nobel Prize. Anyway, I could go on and on about Richard, but I think we'd rather hear from Richard than about Richard. So please join me in welcoming Richard Ellis.
Thank you very much for that very, very kind introduction. It's an honor to be here. I'd like to thank the Brinson Foundation for this series, and I'm honored to be the 10th lecturer in this list of distinguished speakers. I'd like to thank also the University of Chicago for their hospitality for this visit. I'm going to talk about the frontier. So the frontier is very much looking back in time in the work that I do, and the title of the lecture is Looking Back to the very beginning when galaxies began. And it's at a very exciting stage, as I hope I'll explain to you. And what we're trying to do here is use our powerful telescopes to look back in time to a time when galaxies were forming for the very, very first time. Before that, there were no galaxies. The universe was dark, just made of hydrogen clouds. And so this is an adventure, really, to probe right back to our origins, because we are ourselves made of the material that is synthesized in stars, and stars that make the galaxies shine, switched on at some early point in the universe. And I hope to convince you that we are very close to discovering exactly when this happened and the physics that goes around it. So I will, in this talk, I will go through a little bit of a history and where we stand in terms of mapping the evolution of the universe over its 13.8 billion years of cosmic history. I'll then describe to you what it's like to be at the telescope. Sometimes the discoveries are made in real time at the telescope, and that's one of the most exhilarating aspects of being an astronomer. And then I'll bring you right up to date with a discovery that we made, which was published today in Nature magazine. So you'll be right up to date. So you probably know that we live in a galaxy that we call it the Milky Way. This is obviously an artist's impression of what it would look like if we were able to go outside the Milky Way. And you can see that the sun is about 2/3 away out of the center of this Milky Way galaxy. It's a spiral galaxy, so you can see the spiral structure. It has a nucleus that is somewhat full of older stars. That's why it's slightly more orange than the blue stars that we see in the spiral arms. And we've pieced together the geography of the galaxy pretty well. It's somewhat more difficult to do because we're sitting within it. Now, when did all this get revealed for the first time? Well, it's very interesting to go back. Of course, the Milky Way has been seen since antiquity in the night sky, but the first person in recorded history to really figure out what was going on was Thomas Wright of Durham. And he was not a professional astronomer, he was a landscape gardener, but presumably he had plenty of spare time to look at the night sky. And he funded himself a book called An Original Theory of the Universe, particularly the Via Lactea, the Milky Way. And the key figure is this one here, where you see a disk of stars, very similar to that picture that I showed you earlier from that artist's impression. The sun is embedded within this disk. These are all individual stars. So if you look along the plane of the disk, then of course you see a high abundance of stars. If you don't have a telescope, they may not be resolvable, so you see this band of white light. Whereas, of course, if you look at right angles to the disk, you see far fewer stars. And he grasped the idea that this was the physical nature of the galaxy in which we lived in. Now, he might have been a little bit more famous if he didn't get excited by this and he went on. And if you can buy this book, it's a facsimile of it that you can find on Amazon. And if you look further in the book, he sort of gets carried away and he starts placing a supernatural being in the center of the galaxy, and people at that point slightly lost interest in Thomas Wright. But there he is, the landscape gardener who figured out the nature of the Milky Way. Somebody who's much more akin to a modern astronomer in that he used a telescope is William Herschel. Born in Germany but lived most of his career in England, he built his own telescope, several of them. This is what is known as the 20-foot telescope for obvious reasons. It had a mirror that he cast and ground himself, which was about 20 inches across, and he would climb up this ladder and sketch what he saw. And he imagined that the Milky Way was the universe, but he also charted the distribution on the sky of what he called nebulae. He wasn't clear what these nebulae were, but he did in 1789, he wrote, some other nebulae are probably much larger than our own system, and they may be called Milky Ways by way of distinction. In other words, he imagined that there were galaxies outside our own, and this is the first mention that the Milky Way was not the universe, that there were other systems outside. And there was a big debate about this for the next 120 years or so. And it was finally resolved by the man you've all heard of, Edwin Hubble, whose name graces the Hubble Space Telescope. And the Andromeda spiral, which looks somewhat similar to our own Milky Way, was basically, its distance was measured for the first time by Hubble. Here's a photograph from 1923, and you can see in this photograph he's marked particular stars that are seen in the outskirts of this galaxy. And the light curve of these stars, that is their variability, you can see he's written variable here with an exclamation mark. The variation in the light curve of these enabled him to get the distance. These stars are physically pulsating. We understand now why they pulsate, and their period of pulsation links directly with their luminosity, their actual intrinsic brightness. And calibrating this relation within the Milky Way, if he measures the period, he can get the luminosity of these stars, and hence he can get the distance because he knows how bright they are, apparently, on the photograph. Just as if you knew the intrinsic brightness of a lighthouse, then of course just by seeing how apparently bright it is, you could determine how far away it is. So it began to get realized at this point that there was another universe out there, much bigger than the universe that was just confined to the Milky Way. And that's been a pattern in astronomy right from the beginning, starting with, of course, the solar system itself. So we're all big fans of time travel. I'd love to go back in time and see, how the pyramids were built. Maybe you'd like to go back and check that William Shakespeare wrote all of those plays. Astronomers are unique that they can actually witness the past. So when we look at the sun, of course, we're seeing the sun as it was 8 minutes ago. That's the light travel time of a light ray from the sun to the Earth. If we look to the nearest star, we're seeing the star as it was 4 years ago. That's the time a light ray takes to travel to the Earth from the nearest star. But the situation transforms dramatically when we use a powerful telescope like the Hubble Space Telescope. This is the deepest image we have with the Hubble Space Telescope. It represents about 2 weeks of exposure of one small patch of sky. And some of the most distant objects in this image are being seen not as they were millions of years ago, not even billions of years ago, but 13 billion years ago. Now, the universe itself, we think, is 13.8 billion years old. The solar system is 4.6 billion years old, so the universe is about 3 times older than the solar system. And these galaxies that you see in this deep image are being seen when the universe was only 3 or 5% of its present age. So think about it. Encapsulated in this image is a time tunnel. You can't see the evolution of an individual galaxy, but if you can piece together and time slice this image, you could make a movie of how the galaxies have evolved over the vast period of time, over 95% of the history of the universe. So to explain this, I have to introduce the word redshift. And the redshift is a measure of the look-back time because the universe is expanding. So you probably know the universe is expanding. It's very dangerous to think of this expansion as galaxies traveling as projectiles in space. This isn't the model. The galaxies are more or less stationary, and it's space itself that is expanding. And what that does is it stretches the light rays. So if you focus on this lower panel here, you imagine a galaxy and it emits a light ray, for example, towards the Earth, say we're here, then during this light travel time, the space in between these two galaxies has been stretched. And this stretching of the light ray produces the redshift, the stretching of the light. And if we can measure that stretching, we can determine how far back in time we're looking. So, for example, if the redshift is 1 or 2, then the light ray has been stretched by 2 or 3 times. And so we can make a nice diagram of, as the redshift increases, from 0.5 to 1 to 2 to 3 and so far, we can probe the history of the universe right back to the beginning. So here we are today. If we go to a redshift of 1/2, the universe was 4 billion years younger, and the solar system and everything is forming at around that time. And if we go to redshifts of 2 or so, the universe is only 3 billion years old, so very much younger than it is today. So to go back to this image, the key to time slicing this image is measuring the distances and redshifts of all of these individual galaxies, which is a big challenge because they're very, very faint. So how do we do it? What are the tools that we use? So we use, as John said, we use the biggest telescopes that we can. And, you know, it's not that I can just walk up to these telescopes and say, excuse me, can I use it tonight? I have to apply for time, and I have to compete with hordes of astronomers who are all keen to make discoveries with these telescopes, especially the exoplanet people who are, you know, Johnny-come-latelys on the scene. Okay, so here are the twin Keck telescopes, which I used when I was in California. I've moved to Europe, and so we have the European Very Large Telescope. This is 4 telescopes, each one 8 meters across in the mirror. The instruments that we put on these telescopes are enormous. They're still more or less built in universities, but it's right at the limit of what we can do. They're $10 to $20 million instruments. You can see the size of them. And these are the spectrographs that we use to measure the distances and the redshifts to these faint galaxies. And we use space telescopes. And there are 2 space telescopes that are particularly powerful in my talk. There's Hubble, which gives us beautiful high-quality imaging. It's been up there since 1990. It's still doing wonderful work. There's Spitzer, which is a much smaller telescope, an 85-centimeter telescope, but remarkably important and features very much in the discovery that we published today. And then there's the Planck Satellite, which I don't personally use. It's finished its survey now. But it studies the microwave background, which is a subject of great interest in the department here in Chicago. And this tells us a lot about the early universe and the effect of young galaxies on the properties of space. So how do we find these distant galaxies? Well, you know, you might imagine that the faintest galaxies are the most distant. But unfortunately, galaxies come in a variety of shapes and sizes and luminosities. And there are feeble galaxies and luminous galaxies. And so the brightness of a galaxy is a very poor indicator of its distance. So there's a very clever trick, and that is we take pictures of the galaxy in different colors. So imagine taking a picture of the sky in a green filter and a red filter and an ultraviolet filter. And you can see the color of the galaxy. This particular galaxy is prominent in the red filter. It's seen in the green filter. It's a little bit fainter in the ultraviolet filter. This particular galaxy is present in the red filter and the green filter and conspicuously absent in the ultraviolet filter. And the reason for that is that hydrogen absorption in the galaxy and along the line of sight occurs at a fixed wavelength and occults the light of this galaxy. And the reason is this particular filter has found an object that is so far back in time that the hydrogen absorption, which we know occurs at this short wavelength, has been redshifted into this particular filter. This was pioneered by a colleague of mine when I was in California at Caltech, Chuck Steidel. Here's a little movie that makes it very clear. So here's the spectrum, and you can see this absorption is being shifted artificially. The redshift is here. It'll repeat. And you can see the galaxy drops out in each of these filters. So if you can take a picture of the sky in many, many filters and determine in which filter the galaxy disappears, then you can estimate the redshift. And Steidel's work was a breakthrough because it opened up the high redshift universe for the first time, and I remember that was in the mid-1990s. So when I got to Caltech, this instrument, DEIMOS, appeared on the telescope, and we used this color technique to find a galaxy at a redshift of 6. That corresponds to looking back to when the universe was about 7% of its present age. And we detected this glowing hydrogen line at this precise redshift from this particular galaxy. So we've pieced together, via this clever technique and imaging, beautiful imaging from Hubble, a sort of first-order picture of the evolution of galaxies over about 90% of its present age. So today, the universe is about 13.7 billion years old. We have beautiful spiral galaxies. We have these smooth elliptical galaxies. And if we go back to when the universe was about 5 billion years old, here's the redshift, measured spectroscopically. And you can see there are galaxies that look like this elliptical, even at this early time. There are galaxies that bear some resemblance to spirals. They don't look so pretty. But more or less, you could say that they're going to evolve into objects like this. And if you go to the very highest redshift, when the universe was about 1 or 2 billion years old, suddenly things change. The galaxies are physically much smaller. Many of them have multiple components, as if they're merging and assembling into bigger systems. And so this picture now of galaxy evolution is telling us that we're really getting towards the beginning. We're seeing objects that are much more immature and physically smaller, and this is telling us that, this technique, if only we could extend it, would, probe towards the birth of galaxies, and which is the topic of the talk. So I like this compilation of the most distant object. This always gets in the newspaper, of course. So what is the most distant object that we currently know? This is the year of publication. This is the redshift. If you don't like redshift, that's fine. Here's the age of the universe at the time that object was discovered. And when I was a student at University College London, quasars were the most distant object that were known, and it was a very exciting time. But suddenly, when Steidel and others began to exploit this color technique that I just described, you can see slowly we started to catch up, and galaxies began to be found out to redshifts of 6 or 7 or so. So I'm now going to focus on this frontier when the universe was very, very young, and this is where the challenge is, to try to determine, when did all this begin, and that's really, probing towards the birth of galaxies. So it's an unfortunate fact. We live in a world with theoretical astronomers, and you know, we just have to accept that that's a fact. And they always have everything sewn up well before any observations are made. My favorite theoretical astronomer is at it's a very small community college called Harvard University. Probably haven't heard of it, but he's a very distinguished theorist, and he wrote a very nice feature in Scientific American, so I pinched this picture from him. So this is the timeline of the history of the universe, and it's focused very much on this early period. So here's the Big Bang, and the glow from the Big Bang that is this microwave background that this Planck Satellite studies. And about 300,000 years after the Big Bang, the hydrogen atom formed for the first time. As the universe expands, it cools, and eventually the hydrogen atom, the proton and the electron come together, and so we have these dark hydrogen clouds. No starlight, just darkness, and the glow from the Big Bang. But these hydrogen clouds gravitate, helped by dark matter, and they eventually begin to collapse, and they get hot in the center. As the gas cloud collapses, the energy in the potential energy is converted into heat, and in the centers of these clouds of gas, eventually stars ignite. You know that the sun shines by nuclear fusion, and so these stars begin to shine, and the universe is bathed in light, and we call this moment romantically cosmic dawn, when the universe began to shine in starlight for the first time. Now, these stars are very different from the sun. They only have hydrogen and helium. There are no heavy elements, because the heavy elements that make up you and me are synthesized in stars. And this is the first generation of stars. And so they're very hot. It turns out for a given mass, a star with no iron or calcium or sulfur is much hotter than a star today. And so they produce energy, radiation, that ionizes the gas in the space between galaxies. And you see these as these bubbles, and these bubbles grow with time, and they eventually overlap, and the universe becomes fully ionized. So what do we mean by that? Well, originally that's the dark hydrogen cloud, so here's the proton and the electron. But the energy from these young stars breaks the hydrogen atom into its constituents, the electron and the proton. So here's a movie of this, produced, of course, by numerical theorists, and this time from Stanford. And what you see is a cube of space where the hydrogen clouds, these ionized bubbles, are the blue regions. The expansion of the universe has been taken out, and this cube of gas rotates, and you can see these blue regions, like Swiss cheese, eventually start to sort of merge together as time progresses. And eventually the universe transforms from being hydrogen to being an ionized gas of protons and electrons. So I like this movie. Many people have done these calculations. It is a rather slow movie, but this is 500 million years, so you have to be a little bit patient. So the big questions, I think, when we reach the frontier, the questions have to be simple. And, people who work in detail on nearby galaxies often are astonished that we have the audacity to ask these questions because, we know that the universe is probably more complicated than this, but we have to start somewhere. And so one of the big questions is, when did all this darkness end? We call this period the Dark Ages. Astronomers are very good at giving romantic names like dark matter, dark energy, and dark ages. It's very good for fundraising to have these mysterious titles. When did all this happen, and over what period did this ionization occur? And were these star-forming galaxies responsible, or were there some other ingredient necessary to burn off the hydrogen? And the theme of tonight's talk, can we witness this moment when it all began? So I told you that the early stars don't have any chemical elements other than hydrogen and helium. So what could be simpler? You just keep getting spectra and looking to see whether you can identify what we call pristine stars that have no heavy elements. So here are all the heavy elements: carbon, calcium, iron, nitrogen, oxygen, magnesium, and so forth. And presumably, you know, as you go back in time, you would expect to find what we call a primordial gas that just only has hydrogen and helium. It turns out that this is a very risky strategy for finding the first galaxies, because the time window where the stars are pristine is very, very short. Stars explode, and the product of their nuclear burning is immediately injected into the gas, which forms the new stars. So this cycling can happen in only 50 million years or so. So the likelihood of finding an early galaxy with no chemical elements is a bit like looking for a needle in a haystack. And so I think my view is that it's much more likely and much more practical to tie finding the first galaxies to determining when this reionization began, when this process began and ended. And that's where this Planck satellite comes in. So what is the Planck satellite? It is a satellite that looks at the glow from the Big Bang, which we call the cosmic microwave background. And I told you that the breaking of the hydrogen into a proton and electron means that there are free electrons from the moment that this process began all the way down to the present day. So there's a column of electrons here that polarizes, just like polarized sunlight reflecting off the water on the road when you're driving. Exactly the same scattering produces signatures in the microwave background that we can see. And the Planck Consortium put a huge amount of effort into this. They just won a very big prize, actually, this year. And they predicted from their analysis that the hydrogen was neutral at a redshift of about 11 or 12 when the universe was about 500 million years old, and it all ended, the universe is completely ionized by the time the universe was about 1 billion years old. So 500 million years is this transition. And most people seem to buy this result. It's a very important step in constraining when all the... so one would imagine that the earliest galaxies would be somewhere out here if we could find them. So there are two ways to verify the end of reionization, which is where my colleagues and I began to look. One is you can actually penetrate the gas in between galaxies by shining a bright light all the way from a distant object all the way to the Earth. And that's what the quasars can do. The quasars are extremely bright galaxies that have energetic black holes in their centers. And for the purposes of this talk, they're just beacons of light at the high redshift, at early universe. And these are these ionized bubbles. And you could imagine that when the universe is neutral and there are very few ionized bubbles, the hydrogen is in atomic form and it produces an absorption in the spectrum of the galaxy. Whereas when the ionized bubbles are frequent, then you see this spiky pattern. And so one would expect in the line of sight of a quasar to see an evolution of hydrogen absorption from the ionized era into the darkness over here. Here's the actual data. So here are the spectra of many quasars, and you can see indeed broadly that's the case. So let's take this one. You see all of these spikes here, and then suddenly complete absorption. And so via this technique, this is a very, very nice review by George Becker, who's at the University of California, Riverside. He gets the idea that this reionization starts to happen at a redshift somewhere between 5.5 and 6. So if we go back, you know, that's pretty well in agreement with what the Planck people are saying. So what did we do? So we had a different idea. We decided to look not in absorption, but for the galaxies to look at the hydrogen in emission. And the idea is, it works like the following. One of the most prominent lines in the spectrum of hydrogen is, we call it the Lyman alpha line. It's an ultraviolet line. And it's easily scattered by gas if it's in this neutral atomic form. So if the galaxy is sitting in the dark ages where there's neutral gas, then this line is very easily extinguished. Whereas if it's in one of these ionized bubbles, then the line can freely propagate out, and the line is detected. And now I know this is a complicated concept, so I have a Californian analogy ready for you. Here's the freeway, and every automobile is a galaxy. And every headlamp is this glowing line of hydrogen. And you should think of the dark ages as a fog. The cars are still there, but you can't see the headlights of these cars because this line is being dimmed by the darkness of the scattering by this fog as you penetrate further in. So what's it like to do these experiments at the telescope? So these are two students now moved on. So this is Dan Stark, who was a student of mine. He's now a professor at the University of Arizona. This is Matt Schenker, clearly in Hawaii. And he decided to go to Wall Street. And we're going to keep a very close eye on him because he may be able to help us when he gets very, very wealthy. And here's the redshift distribution of our survey. And what we did was to go to the telescope. So one of the most exciting things, I'm very old-fashioned. I know it's possible to control these telescopes remotely, but I find it exhilarating to actually go to the telescope. So this is a Time magazine article from quite some time ago, and Dan Stark is looking suitably animated here while I'm pointing out some discovery to him on the computer screen here. Students can actually control the biggest telescopes in the world themselves. It's an astonishing experience for them to learn how to make discoveries in real time. Now, there is one very big disadvantage of going to the telescope: cloud. And occasionally it's cloudy, and sometimes you can go to the telescope for 3 or 4 nights and it's completely hopeless and it's totally wiped out. So here's the cloudy night photograph. This guy has finished his thesis. He's very, very happy. He's Italian. They're always happy, aren't they, the Italians? Very, very happy. This guy's thesis is rapidly going down the drain, and obviously he's not very happy. And so the job of the professor at this moment is to buy the pizza and the 2 bottles of wine and cheer everybody up. And that is presumably why this photograph is somewhat blurred. Anyway, okay. So what we did was we went to the telescope and we basically looked for this line, this hydrogen line. Here it is. This is a negative image, and you can see the redshift here. And these are heroic exposures. So these are simply exposing for 2 nights on one of the biggest telescopes in the world. And sure enough, we found that the visibility of this line, the fraction of galaxies that show this line that is like a thermometer of the darkness, we do indeed see this drop at about a redshift of 6 or so. And since we did this work, many other groups have confirmed this. So obviously we're onto something. We need to probe deeper. If we could only look even further back in time, maybe we'd start to witness the drop in the number of galaxies. And so in 2012, a group of us with a collaboration, this is at the University, the Royal Observatory in Edinburgh, we took this very, very deep image that I've shown you already. It's called the Hubble Ultradeep Field. It's this 2-week exposure with Hubble of a small area of sky that's about 1/10 of the diameter of the full moon, so 3 arc minutes on a side. And there are about 2,000 galaxies in this image, but these objects shown in these little colored triangles were the most distant objects. And this gave us the first census of galaxies out to a redshift of 10 or so. And I'll bring you up to date in a minute on what we know about these objects. So you may say, well, you know, you've only got, what, 7 objects here. You know, did you really point Hubble for, 2 weeks just to discover 10 objects? Well, it turns out that at lower redshifts, say between 6 and 9, we found in this image 74 galaxies. So we're really building a census of how many objects there are at different epochs. Now, there is a clever trick that I want to introduce now at this point for aiding us in finding objects at very early times. And it's called gravitational lensing. And the trick is that when you point a telescope, whether it be Hubble or the Keck telescope, through a foreground cluster, which has a lot of mass in it, the light rays can be bent by the mass in this cluster and magnified. So it's like a free additional telephoto lens that you can put on the end of your telescope, making it yet more powerful. And this is a way of boosting the signal from these faint objects, making it really very, very powerful. This goes back to Einstein. Here he is. A few years ago, my wife gave me an Einstein calendar. You know, every month there was a picture of Einstein doing something different. You know, in one month he was at the blackboard riding like this. Next he was riding a bicycle. And by the time we got to April, I realized he was always wearing the same suit. So here's the deflection that is a feature of his theory of relativity. And it's 100 years next year. It's the anniversary of the verification of this bending of light by massive objects. Here's the brilliant individual, Sir Arthur Eddington, a famous Brit from Cambridge, who was a theorist, a very distinguished theorist, but decided he was so inspired by Einstein's theory that he became an observer and decided to go on an eclipse expedition and measure the positions of these stars. This is the actual photograph. And compare the position of the stars during the time of the eclipse with when the sun wasn't there at night. And the deflection is a very small effect. It's just a few, just over an arc second, and he became very famous for verifying Einstein. Actually, this observation catapulted Einstein into fame, and we'll be celebrating this next year. Eddington himself was, somewhat had a puckish sense of humor. He was asked by a journalist after this, Professor Eddington, it's claimed there are only 3 people in the world who understand Einstein's theory of relativity, to which he apparently answered, who's that third person? So it's clearly somewhat opinionated. So how does it work? So we have a galaxy here. Here's a cluster which is acting as the lens, and depending on it's very similar to standard optics. Depending on the alignment with the observer, you can see multiple images, so mirage, you can see the same galaxy in different parts of the sky, or you can see just a small distortion, like a stretching. And it also depends on the relative distances between you, the lens, and this. And here's like a simulation of how this works. So what we have here is a transparent lens that's been put in front of the background. I mean, you can see the stretching and the magnification can be, in certain circumstances, if the alignment is perfect, can be truly amazing. And it's just astonishing that neither Einstein nor Eddington thought this lensing had any future applications that would be useful. They thought it was just useful for verifying general relativity. So when I was in the UK, I got very excited by lensing, and I worked with many students and postdocs. Here's a good example of a multiple image. You can see two little images. This is a cluster of galaxies. Here are the foreground. These are the objects that are acting as the lens. These two little galaxies here are, in fact, the same galaxy. They lie well behind the cluster. And the geometry is so precise that you can predict where the third object is, and there is indeed a third object here on the other side. So it's very exquisite theory. Move on a decade or more, suddenly in this particular cluster there are 180 multiple images, and this is a huge industry now. There are postdocs scanning these images automatically to try to find all of the multiple images and build a picture of how this lens actually works, and it's very, very exciting. So back to the theme of the talk, this additional boosting by gravitational lensing has led to its own redshift record, the most distant object, going all the way back to 1988 and bringing you right up to date with the object that we published today by my Japanese partners. And the ones that I've been involved in are shown here in red. So there are these two techniques. We can point Hubble for a long, long time, or we can use this boosting by these gravitational lensing. Here are three images of the same galaxy, A, B, and C, proposed at a redshift of 10. Here's another one, not yet confirmed, three images in this particular cluster thought to be at a redshift of 11. And the good thing is these two techniques agree. So we now have a census of how the number of galaxies is falling off as we go back to the beginning. So remember, the Planck result was that reionization began maybe around here, and you can see we now have, the census of objects. We're not quite there, but certainly the numbers of objects is declining very, very rapidly out to redshifts of 10 or so. So Nick Neden, who's here at the University of Chicago, is an expert on this reionization history, and he predicts that there is a small tail of activity out beyond this redshift of 10, maybe even out to redshifts of 20. And so somewhere in this window here is when we think first light began, maybe from 250 million years after the Big Bang to 500 million years after the Big Bang. Now, I've talked about optical telescopes. There's a new kid on the block, and it's called ALMA. It's the Atacama Large Millimeter Array. It's 66 telescopes at 5,000 meters high in the Atacama Desert. And I'm not a radio astronomer, but I'm very excited about ALMA because it's a very powerful way of looking at gas and dust at very early times. And it's a very powerful big telescope. It's equally difficult to get observing time on it, but we've been working on it. And I now come to the result that we published today. It's basically an ALMA result. It's another one of these gravitationally lensed objects. Here it is. It's very, very faint, as you can see. It's got the romantic name of JD1. And the redshift of this galaxy has been measured very accurately with ALMA from this oxygen line, which it is in itself interesting because remember, oxygen is an element that's synthesized in stars. So if we see oxygen emission at a redshift of 9, then there must have been stellar synthesis before that. It's confirmed with a hydrogen line from the Very Large Telescope. Here's the exposure that we did. It's much weaker. It's much harder to make the measurement in the hydrogen line than with ALMA, which is a tribute to how powerful ALMA is. So we have the distance to this object. It's the most distant object that we know that has two agreeing spectral lines. But there's another side to the story which is very cute, and that is that we have the energy spectrum of this object. And we can tell the difference between the young stars, which shine in the ultraviolet, and the old stars which shine in the optical. And for this, we need this Spitzer measurement, the Spitzer Space Telescope. And you can see the strength of the signal from the old stars is really quite prominent. And we estimate that this galaxy is not recently arrived on the scene, but has been forming stars since about 250 million years earlier, out to redshifts of 15, and hence as early as 250 million years after the Big Bang. So back to Nick Neden's slide here, we're sort of indirectly probing the birth of an object out to this period out here. This is as close to the beginning that we've currently got. None of you like dust. You know, housewives and housemates hate it, and dust is in the universe. It's fortunately not this kind of dust. It's dust that's produced in exploding stars, interstellar dust. And these are mostly small grains that are very, very small, maybe a few micrometers across. But this dust glows. It absorbs starlight and glows at these wavelengths that ALMA is very, very sensitive to. And sure enough, we detect dust from ALMA too. We've done that out to redshifts of about 8.5 or so. And the amount of dust that we can measure is also a measure of how much earlier star formation there is that's been exploding, has produced exploding stars that produces this dust radiation. So let me wrap up with the future. We have, got to the horizon now where we think we see the very earliest objects. We have one galaxy maybe that's telling us that we're very close to finding this moment of cosmic dawn. And we have ready to launch the James Webb Space Telescope, which is Hubble's successor. It's, as you can see, it's a segmented mirror. It's a somewhat larger telescope than Hubble. Hubble is a 2.5-meter telescope. This is a 6.5-meter telescope. But crucially, one of the goals of Hubble is of James Webb rather, is to probe the very early universe. Its wavelength coverage is very, very suitable for looking right into this era of cosmic dawn. And to complement this, on the ground we have 3 very large telescopes that are under construction. One is the European Extremely Large Telescope. They had the Very Large Telescope. Then they had, originally they had the Overwhelmingly Large Telescope. But they couldn't afford it, so they scaled back to the Extremely Large Telescope. And that's this facility here. And then Chicago, and of course Carnegie and others are championing the Giant Magellan Telescope, and Wendy here has been a pioneer in establishing that very impressive facility. And the 30-meter telescope is the other US telescope, which involves partnerships with Japan, Canada, India, and China. So the future is very, very bright, and of course all of these facilities will give us that extra boost of power in order to find these very early objects. Well, you've been a very nice audience. Thank you very much. I should finish with one sort of story about, whether all of this is worth it. I've told you that, observing with students is great fun. Do we really think that this is a worthwhile exercise? And who better to go back to than Edwin Hubble himself, a very interesting man, actually. He was a Rhodes Scholar. He went to Oxford, and he picked up the Oxford accent, and he never lost it. And of course, his Californian colleagues really didn't like this affected British accent. But he wrote a very, very nice piece. He wrote a very famous book called The Realm of the Nebulae, which was published as a series of lectures he gave at Yale University in the 1930s, and it's been reprinted many times, so if you haven't read it, you should. And in that book is, I think, a sort of motto of mine that, that we will keep looking at the dim horizon. We will find landmarks that are very, very faint. The search will continue. It's really exploring, isn't it? It's basically, why we're interested in science. The urge is older than history. It will not be oppressed. Thank you very much.
have time for a few questions, and we have some students with microphones. Any questions for
Hard to
Richard?
see, isn't it? Yeah, there's one at the very back. Yeah.
Can't see.
Can we put the lights?
Yeah, here it comes.
Okay.
Here comes the microphone.
He's a microphone guy.
Hi. I'm training to be a teacher, and I'm curious about students and like the general public. And I'm wondering if you, like with the advent of all the technology we've got, like is there a potential for the general public to become the students of cosmology?
Yes, so there are many projects where data such as the data that I've described is being used in citizen science experiments where people can join directly in the searches for example, these gravitational lenses are really exciting to find. And so there are various projects. There's a particular one that's run from Johns Hopkins University and Oxford University, which takes and trains members of the public to actually explore as part of the surveys that we do to find, for example, remote objects or catalog galaxies and so forth. And these citizen science programs have, in some cases, thousands of people inspired, and they teach one another, through social media and through the internet. I think, in particular, it's very important to get to the young students, the school children. And one of the most interesting studies that I remember recently was they did an analysis of undergraduates that were in any topic in science or engineering or math. And they asked them what was, if you go back to when you were, say, 10 or 12, what was the topic or what made you decide that you might be interested in doing, a STEM-based university course or get into that area of employment. And astronomy was number one. The black holes, the Big Bang, time travel, the distant universe. Those were even though they didn't become astronomers, it got them inspired in big questions. And so I think, we have a duty, to reach into schools. And so certainly there are programs in the UK, and I know in the US too, to do that. Did you have something specific in mind?
Not really. I feel we misuse the tools that we have in our hands so often, and without guidance from teachers, there's a large break.
So this is more training teachers then?
I'd love that. Yeah, I think that's great too.
Yeah.
Just
Thank you.
Bridging the gap.
Other questions?
Yes, right over there. Yeah. I'm looking into the fog, it's just like the dark ages.
Yes, I'm only about 2 billion years away. Is light the only tool you have to work with for these kinds of questions? Is there any use of the gravitational wave detection or anything other than light, or is it pretty much all light all the time?
I'm sorry, the reverberation is really strong. Can you maybe hold the microphone a bit lower?
Is this better?
Well, maybe a bit, yeah.
Is light the only tool you have to work with?
Oh, is light the only tool we have to work with?
Yeah.
So there's a theme I didn't have time to cover. It was one of my questions, and that is the radiation from stars the only possible explanation for this burning of the hydrogen into protons and electrons? And the answer is no. There is a possibility that there are black holes in these galaxies. Now, I talked about quasars. What is a quasar? A quasar is a galaxy with an enormously massive black hole in the center. We're talking about a black hole that's several hundred million times the mass of the sun, in some cases a billion times the mass of the sun. These quasars are found out to when the universe is only 800 million years old. So how did those black holes get there so quickly? And the answer may be that these black holes are formed independently of the galaxies. This is a conjecture at the moment. So how could we test that? Well, in principle, with the most powerful gravitational wave detectors. You had a very nice lecture here a year ago on gravitational wave. astronomy, that whole subject has really exploded. There's so much interest in it now. With an upgrade to their current gravitational wave detectors, it would be possible to see merging black holes in this early period of cosmic history to determine whether there's a separate route of forming early objects like black holes. And the radiation from black holes, if they gather gas clouds and the material falling into the black hole, can be an extraordinarily powerful way of burning off this hydrogen. So gravitational wave astronomy is not quite yet at the level of precision and sensitivity that we can go back to these early times, but the progress is very, very exciting.
Additional questions?
I think. Yeah, here.
Oh, here we go. The microphone?
Right at the front.
It's very hard to see through the fog here.
Hi. I'm wondering, so you told us we can see far back in the future.
Yeah.
Is there either the possibility of predicting the future or knowing the future?
Okay. We can predict statistically, what is likely to happen in terms of galaxies, and it's not very exciting. It's a bit depressing. So eventually, the bottom line is the galaxies are running out of gas. And so the stars that we see around us today will eventually die. And the fuel that would produce new stars is getting less and less and less. So galaxies are going to get darker. Of course, there'll be the expansion of the universe, as you heard, is accelerating. So galaxies are getting further apart. So the future looks pretty dark. Now, the good news is that there is a very poor understanding, despite the Nobel Prize, of exactly why the universe is accelerating. We don't know whether this acceleration is a permanent feature of the universe or whether there's some remote possibility that this acceleration would eventually decay or switch off, in which case the universe might stop expanding. This is pure conjecture, but doesn't seem to stop theorists from writing papers on it. Okay, I wouldn't want to predict the future, and don't worry, it's not going to get dark for many billions of years. So,
Not in our lifetime, no.
Yeah.
Thank you.
Okay.
One last question.
So one other question about the future. What is, for the young astronomers, astrophysicists in the audience, what's the prospects for employment in the future?
In astronomy?
Yeah, it's always a challenge, and believe me, it was a challenge in our careers too. I didn't get the first job I applied for, I didn't get the second one either. The message is to keep optimistic and keep trying. The United States is actually in a much better position than many other countries, actually, in terms of employment. It is very important, I think, to realize that when you enter a PhD, that it's not a straightforward path to a career in astronomy, and that's never been the case, actually. It's always been that if you do a doctoral degree in astronomy, it trains you, just like that Schenker guy who went to Wall Street. They love him, because his analytic skills have been honed at my expense, which I keep reminding him. The hedge fund company loves him because he's learned to deal with imponderables, and he's had tenacity. So I don't think we should feel embarrassed that not everybody that gets a PhD gets a job, because we're training people to contribute to society in many, many important ways. Now, I know everybody would love to be a professor because, in my opinion, it's the best job in the world, a university professor. But, it's a fact that, only only a fraction of the PhDs can make it. But they should remain optimistic. Very few of them, almost negligible number, don't get a decent job. So, you know, it's not time to be depressed when you're doing your PhD.
Well, let's thank Richard one more time for a wonderful talk.